Welcome back. This is lecture 32. So up until now, we have been discussing various aspects of RF design. We have covered metrics of how to characterize an RF system, what are the different things that you need to take care. Among the blocks, we have talked about LNA, and we also covered with some amount of detail about passives and the issues with matching networks, right? And what to do if we have losses in the matching network. Now it's time to step on to the next part, that is, what is the next block in a radio receiver after the LNA? It's generally the mixer, right? So that's what we are going to start today, right? Okay. So now again we have an antenna and we have an LNA. Now what is an LNA in principle? An LNA is a element, is a block which obviously has to take into account matching. So I'm assuming matching has been taken care. It's an amplifier, right? But in principle, is it a voltage control voltage source, or it is a voltage control current source? The way we went about designing the LNA, at least the one single configuration that we saw in detail, was having a high output impedance, right? If it is a high output impedance, then it's more of a voltage control current source than a voltage control voltage source, and that's what we are going to assume, right? So again, so we are assuming this is a voltage control current source. Put a sign of negative because it was a common source configuration, so you have an inversion, and we assume that input is matched, right? The matching is assumed. I'm not explicitly showing it here. At the output of your LNA, we had a load, right? At resonance, it behaves like a resistive load, but nevertheless you have a load, right? So you have a load. Okay. So now what we need a mixer, right? So we need a mixer, and the mixer ideally should be a single tone mixer, right? So which means this ideally should be a sinusoid at the frequency of FLO, where FLO is the local oscillator frequency, right? Again, the assumption is that the input is at FLO plus FIF, right? Where IF is the intermediate frequency. We are assuming we are dealing with a heterodyne receiver. Okay. So if that is the case, the output of this of the mixer should have components at 2FLO plus FIF and at FIF, and if I low pass filter it, right, so that such that the low pass filter's cutoff frequency is near FIF, right, just greater than FIF, but less than, much less than 2FLO, then at the output you are only going to get a signal of FIF, which essentially is your radio receiver, at least the first stage of the radio receiver that we desire. But the issue with this particular configuration is we cannot get a sinusoidal mixer easily, right? But there are other, at the beginning of the course, we talked about some other ways of getting around this problem. What were the other possible ways of making a mixer? So in the current domain, we saw that if I have a current that is coming in, say I have a current, some current I in that comes in, right? And let's say I multiply it with a square wave of time period TLO, then the output will naturally be, if we call this ST, the output will be I in times ST, right? Which naturally means that the frequency component of I in times ST will be the frequency of I in convolved with the frequencies of ST, and since ST has a finite, has a non-zero strength at FLO, right? So then we kind of get a mixing operation. But the issue is we are going to get a lot of other harmonics also, other sidebands, because of multiple sidebands of S of t, which we need to take care of. But how do I multiply? If I said that it's not simple to multiply or design a multiplier, an ideal mathematical multiplier with a sinusoid, but how do I get this S of t? It's fairly simple. We have seen this before. So let's say I have a current source, which is this LNA voltage control current source. Let's say current is going out, and don't bother about the direction for the time being. If I, let's say, have a switch, and the switch is being driven by ST, where ST is a square wave of time period TLO, then clearly the current that is going out here, and assuming this is a short circuit current, right? So let me call it ZBB, because this is baseband side, right? So assuming the impedance looking in here is Z mix, and this is ZLNA. So if Z mix is much less than ZLNA, and the switch ST is on, right? So this is 0 to 1, and the switch ST is on, assuming it's an ideal switch with 0 on resistance, then naturally all the current, all this ILNA current will tend to flow through the switch on the other side, right? So this is I mix. So the I mix current will be equal to ILNA, right? So if this condition is met, then if ST is equal to 1, that is the switch is on, then I mix will be equal to ILNA, right? And if ST is equal to 0, then I mix equal to 0, correct? So the current that is flowing, that is I mix, is nothing but ILNA times ST, right? So therefore I mix is ILNA times S of t, correct? Okay, so hence we have a mixing operation. But now we have to be careful, because S of t not only has component of FLO, it has many other components also, right? So let's see what are the potential issues that can arise. Okay, so let's draw out the spectrum. So firstly, note that let's take a different page. Note that we are talking about a case where you have a non-zero IF, right? So your ILNA has a frequency component of, if this is FLO, your ILNA has a frequency component of FLO plus FIF, correct? Okay, so this is F. What about ST? What components does ST have? So ST clearly has a DC component, right? ST has a DC component. I called it, let's say, C0. ST will have a component at FLO, right? ST will have a component at FLO. If S of t is a 50% duty cycle, where will the next component be? Will it have a 20 component at 2 FLO? No, it will not, right? So the next component will be at 3 FLO. This will be somewhere here, 3 FLO, and so on, right? Similarly, on the left hand side, on the negative frequency also, so I call this C1 on the negative. Similarly, on the negative side also, I'm going to have a C negative 1, and they are going to have something at C negative 3, and so on, right? But and we earlier saw that C1, magnitude of C1 is identical to that of C negative 1, right? So when you multiply these, right, what's going to happen? So for the time being, let's ignore these effects of, okay, let's not ignore, right? So if we ignore, then it won't make sense. So let's take everything into account. So what's going to happen to I mix, spectrum of I mix? So clearly, the first thing is this FLO plus FIF is going to convolve with C naught, right, and create a tone at FLO plus FIF, right, and the tone strength will be C naught times, if this is VPP, C naught times VPP, right. Then this guy will convolve with C1, and where will it create a tone? It will create a tone at, the way this is FLO, it will create a tone at 2 FLO plus FIF. So FLO is here, 2 FLO is here, so this is 2 FLO, FLO. So 2 FLO plus FIF, it is going to create a tone. This will be C1 times, this is 2 FLO plus FIF, this is C1 times VPP. Then this will convolve with C negative 1 and create a tone at FIF. So that is the one that we are most interested in, right. So this is C negative 1 VPP at FIF, right. So similarly, it's going to also convolve with 3 FLO, right, and it will create a tone at 4 FLO plus FIF, that is like way out of the picture, and it is going to create another tone at, I have this negative 3 FLO here, right. Right. So it is going to create a tone at FLO plus FIF minus 3 FLO, right. So which is negative 2 FLO plus FIF. So this is 1 FLO, negative 2 FLO somewhere here, right, negative 2 FLO, and so on. Okay, so note that I have only now considered the case that where you have an input at FLO plus FIF, right, but we know that you are going to have a tone at the negative frequency also. You are going to have a tone at minus FLO plus FIF also, and correspondingly you are going to have tones here. You are going to have tones at this minus FLO plus FIF is going to convolve with plus FLO, and you are going to have tone here C1 times VPP, right. Actually, I should not say VPP, I should simply say VRF, right, because if you think about it, this VRF, the strength of the sinusoid, if you divide it into two bins, it gets divided by 2, right. So here we are not particularly bothered about whether it gets divided by 2 or not. I am just calling it VRF. Assume that it has been divided by 2, right. Okay, so let me get rid of these terms. So now the key thing to note here is whether here also you are going to have another one, right, minus FLO plus FIF, you are going to have C0 PR. Okay, so what is the desired tone? The desired tones are, these one are the desired tones, right, at FIF and negative FIF. These are the desired tones, because that is the intermediate frequency that we are after. Everything else is undesired. So ideally we would like to have a filter which filters out everything else and keeps these, correct. Okay, so now what problem do you see? So what is the nearest tone that determines the steepness of the filter? Clearly this is the tones at FLO plus FIF and the tones at minus FLO minus FIF are closest to the desired band, and they also need to be filtered out, right. So hence if you make a mixer which simply multiplies the input with s of t, granted you are going to get these granted you are going to get your FIF, but you are also going to get a strong presence of a strong presence around FLO plus FIF also, right? So basically this is the input directly coming through, right? So your antenna had a input at FLO plus FIF. The whole idea of putting a mixer is converting that FLO plus FIF into FIF, but because of this tone, because of the presence of this tone, you are seeing the amplified or a scaled version of the input signal directly coming through, correct? And depending upon the gain of the mixer, this can be pretty high, right? And note that this is now depends upon how far it is of FIF. If let's say FIF is 10 megahertz and FLO is let's say 1 gigahertz, I mean it's about 2 decades away, correct? What is the level of filtering that you need to achieve? You'll have to decide whether this is acceptable or not. An alternative solution can be to come up with an architecture which completely gets rid of this tone, and in order to do that, what we need to do, we basically need to manufacture a waveform or manufacture a way of ensuring the C naught is equal to 0, right? If we can manufacture a way of ensuring C naught becomes 0, then that tone doesn't really exist, right? So then the first tone that we have to deal with is this guy, so which is at least slightly further away, right? 1 FLO away. So I can probably get away by using a shallower filter, or even if we use the same kind of filter, then I'll get decent amount of rejection due to these sidebands, right? Okay, so the next thing to discuss is how do we go about getting rid of C naught, right? Okay, so by the way, this type of mixers where the component of the input directly comes through are often called single balance mixer, and the one that we're going to study next, where we'll see if we can get rid of the C0 term, then these are called double balance mixer, right? So I mean, in most cases, for obvious reasons, double balance mixers are the one that are usually preferred, right? So let's see what is causing all this, the effect of C0 to creep in, right? Okay, so now if you think about it, what is happening is, what if I write out the component values that are responsible, right? So which component values are we mostly interested in? Obviously, we're interested in C1, C minus 1, and we are interested in C0. The other ones are far apart, so we are probably not necessary. I mean, they are farther than FLO plus FIF, and hence we are not dealing with them directly at the moment, correct? Okay, so let's only talk about these components, which is I have components at C0, I have components at C1, I have component at C minus 1, right? So by the I'm not writing out explicitly what the location of the sidebands are, but we know, right? Okay, fine. So when we have an input, that is ILNA, right? So your C0 is positive, right? And let's say C1 is positive, C minus 1 is also positive, correct? What happens if I have a input of negative ILNA, right? So the component corresponding to C0 is also negative, C minus 1 is negative, and this is also negative, right? Okay, right? So in a way, having a negative input of LNA also probably will not help. But then we also have to understand this fact that you have an ST, which we assume to be 50% duty cycle, which means there is an option to have or let me call this S bar T, SBT, where ST is 50% duty cycle clock and S bar T is the inverted version of that. So if ST has a, I can express ST as C0 plus summation of Cn e power j n omega LOT, summation over all n where n is not equal to 0, right? So then what can I, if I write it out as C0 plus C1 e power j omega LOT plus C negative 1 e power minus j omega LOT plus a higher plus other power. So let me write it out cleanly so that it will make proper sense. So I can express this as plus higher powers. Then what will SB of t be? SB of t will also be, I can express SB of t as S of t minus TLO by 2, correct? So if I express that S of t minus TLO by 2, I can basically say this is equal to C naught plus summation of n not equal to 0 Cn e to the power j n omega LO t minus TLO over 2, right? So which means that your SBT is C naught plus C1 e power j omega LOT times e power minus j omega LO T LO by 2 plus C minus 1 e to the power minus j omega LO T times e to the power plus j omega LO T LO by 2 plus higher order terms, which is nothing but C0 plus this term remains as is, but this is e power j minus pi, which is essentially minus 1, right? So this becomes C0 minus C1 e power j omega LOT minus C negative 1 e power minus j omega LOT plus a higher order terms, right? So now things are getting interesting because now if I multiply ILNA with S of t, I am only writing out the terms, I get C0 plus C0 plus C1 plus C minus 1. But if I multiply ILNA with SP of t, I get plus C0 but negative C1 and negative C minus 1. Correct? So in principle, if I do subtraction of these, if I subtract these two, then I should be getting rid of C naught, and I only get C1 and C negative 1, which we actually want, right? So this can be done using another block which takes these inputs and subtracts in certain way. And I mean, if you have done analog circuit courses, you know that amplifiers are essentially takes two input voltages and amplifies the difference between the two. Differential amplifiers can be used, but what we would like to do here is not use amplifiers to do this subtraction for us. Amplifiers will be required later on. We'd like to explore an option or whether there is another way of going about doing it. Okay, so let's see, right? So if you have a differential circuit, right? If you have a differential circuit, then generally you can have, let's say you have an LNA, you have an antenna, you have an LNA which gives you ILNA current out. If you have another LNA of identical polarity, right? Basically copy paste of the same LNA, and if the input is minus V in, this is plus V in, then the current that it is going to flow push out is minus I ln A. Correct? So why are we doing all these things? We are doing all these things because if we have this minus I ln A available, right? So then if we multiply it with the same ST and SB of t, what do I get? I get minus I ln A times S of t. If I do, I get negative C naught, negative C1, negative C minus 1, and minus AI ln A times SB of t, right? I get negative C naught, positive C1, positive C minus 1, right? So the reason we are doing all these things is, as it turns out in analog circuits, adding currents is the easiest job of all, right? If you have two current sources, all you have to do is connect the terminals together and the output will be a summation of the currents, right? And the reason we are doing all these things is because we started off assuming that we have an LNA which is pushing current into a switch. So I have a voltage control current source. It's essentially a current source which is pushing a current into the switch. So if you have another copy of it which also pushes a current into a switch, then I simply add up those wires. Then the summation of the current through the wires is basically the current that is coming through each of these two paths added up, right? So that's the whole idea. The summing is much easier in currents, right? If you have to subtract, then you have to first flip and then sum. Okay, so that's why I am trying to flip it I am trying to flip the direction of the current by using a separate LNA, right? How we are going to do it, I'll talk about it briefly later. But let's assume we can flip it. Then I essentially get these four streams of output that is coming out, right? This is stream 1, this is stream 2, this is stream 3, this is stream 4. And if I want to get rid of C naught, which two, and I want to retain C1 and C minus 1, which one should we add? Clearly I have to add these two, right? And I have to add these two. Okay, if I do this, then this will have no C0. I'm going to have plus C1 and I'm going to have plus C minus 1. Here I'm going to have no C0. I'm going to have minus, or rather it's plus 2C1, 2C minus 1, minus 2C1, minus 2C minus 1. Okay? So if I am able to do this in current domain, then I am getting rid of the zero term, C0 term, and I am getting that C1, and not only C1, I am getting a double that of C1, right? So now the question is, how do I go about doing this? So for this, if I have an identical LNA, say I have an identical LNA, all I have to do is take the input and then transform the input into a differential signal. And how do I do that? Now recall that if I have a transformer, let's assume you have an ideal transformer, right? If you have an ideal transformer, I am replacing these with its voltage equivalent. So I have this, and note that all of these have termination, they are matched, right? I mean, there is a matching impedance associated with each of the input of the LNA. So if I use an ideal balun or a transformer, then obviously here I am going to have a plus, here I am going to have a minus input, right? So if I am getting if this is V1 between these two terminals, and if it is like 1:1 transformation ratio, then this will be V1 by 2, this will be minus V1 by 2. So the current that is going to flow out will be Gm times V1 by 2. This will be minus Gm times V1 by 2. Correct? And then what I am doing, I am passing it through a set of switches. One is S of t, one is SB of t. This is also passing through S of t, one is passing through SB of t. And which wires are we connecting? I am connecting the where that connects this one ILNA S of t with minus ILNA SB of t, right? So basically this is your you are basically adding up these two words, just join them and you join up these two words, right? So the current that you are going to see in this various, the current that you are going to see in this various will have the components of, so the C0 will not be there, then you are going to have C1 times whatever V1 by 2 or GM times V1 by 2, the amplitude of that, right? The amplitude of that, and here times 2, sorry, times 2, and the other component will have C minus 1 GM times V1 by 2 times 2, and obviously you are going to have other terms, right? Which are the terms which I have not talked about? You are going to have, you can have the component corresponding to this 3FLO, right? This 2FLO plus IF and so on, right? So these terms can also, not can, will also come in, but they are not the closest terms. We have been able to get rid of the term which was giving us trouble, and that term was this C0 term, right? So similarly, in the other branch is going to have 0. This will be minus C1 GM V1 by 2. The amplitude of that times 2 is minus C minus 1 GM V1 by 2 times 2, right? And the location of these tones will be at FIF. This will be at, so you are going to have C minus 1 at FIF and C1 at negative FIF. So this will be at this will be at FIF and this will be at negative FIF. Similarly, this is going to be at FIF. This is going to be at negative FIF. Okay. So this type of mixer is called a double balanced mixer. This is called a right. Whatever component existed at the input of the mixer, right? So essentially, it's similar to, you can think of it similar to an LO feed through, right? So just the input cannot really feed through because you are cancelling them out, right? So this type of mixers are also called passive mixers because in principle these switches are not giving you any gain, right? If I say that this is the mixer that I have, let's say this is the mixer block. So all it's doing is shunting the current from one branch to another and then adding them up in certain ways, right? So there is no gain per se that this particular mixer block is giving you. So that is why this type of topology is often referred to as a passive mixer. Now, when something is a passive, you obviously know there is something that is there should be an alternative that is active, and that also has similar principles. Just that after the LNA, let's say this is the LNA, you instead of feeding it directly to the switches, you pass it through a voltage control current source, right? So maybe the LNA does not have enough gain. Depends on the particular application. You pass it through a voltage control current source. Now, what is the simplest voltage control current source that you can think of? It's again a common source amplifier, right? And then this current is basically, if this I call this VLNA, this is GM times VLNA. Similarly, if you have a negative VLNA, you have VI. If this is VI, this is minus VI, then you are going to have a negative VLNA, which you can feed it to the other side, and then you have, this is minus GM times VLNA, and then you do whatever we have done just like now, right? So you pass it through two sets of switches, this guy, you pass this guy also through two sets of switches. Let's call this one S of t, SB of t. This is uh, S of t, SB of t, and let's see which one we connected. We connected the S of t in one branch to SB of t of the other branch. So basically, I should join these two, and I should join these two, and then I take them out and maybe pass it through a low pass filter, right? And that essentially becomes your another form of, this is an active mixer, and this also is a very popular topology. It's called a Gilbert cell. This entire thing is also called a Gilbert cell topology. Is also called a Gilbert cell, named after its inventor. Right. So you will see this Gilbert cell topology is used at multiple places also. By the way, one thing that I forgot to mention, but I have mentioned it multiple times in the past, is the fact that once in this interface of in the interface between the LNA and the mixer, do I require matching? So here I know there will be a matching network, right? There, because they have an antenna and balun and whatever. So we need a matching network. Do I need a matching network here? In general, no, because if you are working at like less than 10 gigahertz or so, and this entire stuff is inside the chip, this is within the chip, then in principle the distance between the LNA and the mixer is not a significant fraction of the wavelength, and hence even if there is reflection, you don't care, they are going to overlap exactly constructively on top of each other, and you do not essentially need matching, right? But let's say you are making LNA chips, isolated LNA chips and isolated mixer chips, right? And where each of these modules are going to sit on a board, and you are going to connect everything on the board together, then obviously each of these interface will require matching, right? So at the beginning of the course, I mentioned that this is about integrated RFIC design. We are not doing discrete level design. So we will assume that once a signal comes inside and it is no longer interfacing with the rest of the world, you do not have to bother about matching. We treat it like an analog circuit, right? So that's always good to keep in mind. The another stuff that we should also take care, I mean, it's probably better to get this clarified, is the fact that here I assume that if Z mix is much lesser than ZLNA, if Z mix is much lesser than ZLNA, all the current from ILNA goes into the switches. But that need not necessarily be the case all the time, right? You can as well have a scenario in which ZLNA is lesser than, for the in-band signals, your ZLNA is lesser than whatever lies on the other side of the mixer, right? So no harm done. You can still have S of t, SB of t in the same way. Just that for the in-band signal, now it will behave like that for in-band signals, the current will flow into the ZLNA and it will create a voltage here. And here you are going to observe that voltage at different points of time, right? In a current-driven mixer, right? The current was going in, and we are hoping that there is some impedance on this side, and the voltage was getting formed across the impedance on the baseband side, right? So this is the baseband side, and this is the RF side. Why am I calling this baseband side and RF side? Because if you think about it, here I have the requirement of the signal here is FIF, and the signal that I am getting here is FRF, right? So I am on the right hand side of the mixer, for the receiver configuration, I have low frequency signals, right? Here I have low frequency, here I have high frequency. Okay, so if it so happens that you are generating, your ZLNA is much lesser than whatever impedance that you were seeing on this side, then you are going to see sinusoidal waveforms on the LNA, and looking from here, you are only going to tap out that portion of the sine wave that you are observing on the other end of the switch. Okay, this is a minute difference, but it's an important difference to appreciate, right? Because if you that will help you understand what type of load that you would like to choose on the baseband side, right? For example, since we are talking about loading, so let's say we have this kind of load. Now I am not showing the alternate path. You assume that the same thing exists on the other side. So let's say the current goes in, and I assume that the impedance on the baseband side is much lower than the ZLNA. If that is the case, I would want the entire current to flow into a short circuit, right? So ideally a short circuit, but if it flows into a short circuit, then there's no point, right? I mean, I will not get any voltage. But it need not necessarily be an absolute short circuit. It can be a virtual short, right? For example, I can put in an amplifier, an op amp, and pass it through a resistor, right? Let me call it RF. So if I am having I mix, so this voltage is going to be I mix times RF, negative of that, right? Similarly, I can have another op amp here, that can generate baseband voltage on the other arm, right? So, but now what about filtering? Now note that here we are not talking about, we have not yet bothered about filtering till now, and we have just simply assumed that the filtering can be done some way or the other, right? So what have now let's talk about filtering in a slightly different way. So let's say we do not have this op amp, right? Let's say we do not have this op amp. What if we had have only capacitors here, right? What if we only had capacitors here? What would have happened? So if we are talking about signals which are, so the current that is supposed to flow through, the current that is supposed to flow through will have what type of frequency component? So let's see where are we drawing the frequency component. It was supposed to have a frequency component of FIF, of course, right? It was supposed to have a frequency component of FLO plus FIF, but FLO plus FIF I am cancelling off because of my double balance thing. So then I would have components of 2FLO plus FIF, right? Okay. So now let's first consider this component of 2FLO plus FIF, right? So if we assume that, now where is this current component flowing into? This current is flowing into a capacitor. This capacitor, I call this CBB because it's a baseband capacitor. So this current is flowing into this capacitor CBB, and what voltage will it generate? By the way, this is out of band, right? This is unwanted. I should rather say this is unwanted. Spectral tone coming out of other components, right? This is unwanted. So at this when this current flows into, what is the impedance flows into CBB? What is the impedance that is going to see? So CBB will give an impedance of 1 by 2 pi times 2FLO plus FIF. I'll just ignore FIF because FIF is much lesser than 2FLO. So 2 pi times 2FLO times CBB, right? if I have a current which has a, if I have higher order of, if I have 3 FLO plus FIF, let's say if I have 3 FLO plus dot dot dot, then the current that is going through is going to see a same capacitance, but now the capacitance is going to provide an impedance of 1 over 2 pi times 3 FLO times CBB. So as you can clearly see, as we are dealing with higher and higher sidebands of S of t, these components are coming because of the mixing of various, because of mix. So 2 FLO plus FIF arose because 3 FLO of our, the 3 FLO component of our S of t got mixed with the FLO component of the input signal, right? So similarly, we can have 4 FLO doesn't exist. So let's say I have 5 FLO. The 5 FLO component can mix with the FLO component or negative FLO component and create 4 FLO here. So I'm going to have a 2 pi times 4 FLO by CBB inverse will be the impedance provided by the capacitor, right? So this is a Z at 2 FLO. This is Z at 4 FLO. Correct? So as you can see, as we are moved, as we go to higher and higher frequencies, this capacitor is effectively shorting out signals or unwanted components, right? But if we are talking about, what about the FLO component? When you are talking about the FLO, or rather, what is the desired component? The desired component is FIF. Now, if FIF is sufficiently close to DC, right, the capacitor is essentially giving it an open circuit, right? The capacitor is essentially seeing an open circuit. So, it's providing an open circuit, right? So, this is much less than FLO. So, then your the impedance provided by the capacitor in this case is 1 by 2 pi FIF times CBB, which can be in principle much less than this ZLNA. Right? If that is the case, the FIF, the voltage that you are going to see, right, the signal swing that you are going to see, what are the corresponding input that was giving rise to this FIF? So this component at FLO plus FIF or FLO plus minus FIF was giving rise to this component of FIF. Correct? So which essentially means that this component of FLO plus FIF is going to mostly flow through the ZLNA and create a voltage swing at this node, right? And the rest of the signals, that is FLO, 2 FLO plus FIF, 4 FLO plus FIF, are going into the capacitor and get filtered out, right? So this is essentially selective filtering. This gives you a filtering of undesired signals, while the signal swing across the LNA will mostly be comprising of the desired part of the input, and which essentially means that this entire contraption will almost seemingly look like it has only a single tone of, at the output of the LNA, it will seemingly look like it is a single tone of FLO plus FIF, and also across these baseband capacitors, it will seem like only the FLO plus FIF or only the FIF component exists and the others have been filtered out. Now, it will never be fully filtered out, right? It will only have, the attenuation will be as much, will be corresponding to the value of CBB, but you get the idea, right? You are going to see a lot of swing at the majority of the signal swing across this capacitor will be because of the desired FIF, and 2 FLO and 5 FLO, 4 FLO and so on will get sufficiently attenuated, right? So mixer design essentially boils down to deciding on these component values, right? And some other architectures. The whole point of mixer design is that you cannot design mixer in isolation. You have, whenever you are designing a mixer, you have to understand what type of filtering the mixer is expecting. So based on that, you decide your topology, right? So once you have decided on this entire contraption of the mixer plus filtering, then you put them together, right? So I showed you one example of this. In the next lecture, we are going to continue this, and I am going to talk about some other intricacies of mixer and take it from there. Okay.